This is Dr. Carroll. This is a continuation of the greedy algorithm exercises. Let's talk first about Huffman codes. First, let's talk about how they're calculated, why they're used, why is the greedy algorithm. So to lay a foundation about what we're talking about, let's first talk about where it came from. David A. Huffman in 1952 published a paper with the following algorithm to obtain an optimal solution following a greedy algorithm. First, we're going to assign each character to a node, making a tree with just one node. Then we're going to assign the frequency of the character as the weight. In step 2, we're going to combine the two trees with the smallest weights as children into a new tree and assign the weight of the new tree to the sum of the weights of its children. Step 3, we're going to repeat step 2 until all trees are combined. So what's the application of Huffman codes? We can use it in file compression. Why is the greedy algorithm? Because it looks at just the set of characters that have the lowest frequency. We have one decision through each iteration through there. And so if we're going to apply this, for example, to the next problem, to a large corpus and then each character, we could make a tree for each letter in the file, set the weight of the tree equal to the number of occurrences, and then combine the two trees with the lowest weights by making a new node. Let's see that here for the most common 8 characters in the King James Version of the Bible, and ignoring case. Not surprisingly, space shows up more with 745,000 occurrences, followed by E with 411,000. So the first thing to do is create our nodes that are the trees with one node for each of the letters. And so I've arranged them here in ascending order. And so then the next step is we're going to combine the smallest two trees. Well, that's going to be the trees S and I. And so I've combined them here and placed the weight for the new tree as the sum of the two frequencies there. Now we look for the next smallest two. Let's see, 382,000, 224,000, 242,000. It's going to be N and O here. So we're going to combine those into a single tree. And now we're going to look for the next smallest two. It's going to be the trees that hold just A and H. Now that we've combined A and H, we're going to look for the next smallest two. And notice here that it is the single letter T, but it's also the tree with S and I. So we're going to combine those with the smaller one on the left to create a larger tree with those as children. We're going to continue, and we're going to take E with the tree for N and O and combine that to get a larger tree. And now we're going to combine the next smallest two. Well, that's going to be A and H and the first tree here. And then we're going to combine the next smallest two, and that's going to be space. Interestingly, space doesn't get absorbed in until the end. That's going to have the advantage to have smaller encodings. Now we just have two trees left, so it's trivial what to add. We're going to combine those into one tree. And then what we can do is we can place 0 for all of the left children to figure out what encoding we should use, and 1 for all of the right children. For example, A would be encoded as a 0, 0, 0. S would be encoded as 0, 1, 1, 0. Notice they don't have the same lengths. Space, for example, is just 1, 0. It's the only one with 2 characters. All else are going to have 3 characters. So let's go back to our table with all the counts here. Let's put in our codes. As I mentioned, space would have a code of 1, 0. And then E, we could follow it. We can see that just at the top of the page there, we're going to go to the right, and then to the left. So 1, 1, 0. T is we're going to go left, right, left. For H, we're going to go left, left, right. A, as I mentioned, left, left, left. O is right, 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 right. N, right, 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 left. I is left, right, right, right. S is left, right, right, left. Those are the codes we're going to use. Now this is where we gain our efficiency, is that the total number of bits. Notice while space is the most common character, it has the shortest code, and therefore the total number of bits for encoding it is just under 1.5 million. So the total for all of those is about 8.7 million, 8.8 million. Now this is in contrast to if we didn't apply this encoding, we would need to use 4 bits for every letter, giving us 4 bits times the count of 2.8 million. We're going to have total bits as 11.5 million. So we've saved a considerate portion here by optimizing for the more frequent characters that we have. Let's talk about some more exercises. Let's assume that we're given the following jobs: J sub 1, J sub 2, J sub 3, J sub 4, with times required for their execution, 7, 8, 2, and 1 respectively. In what order should they run to minimize the average time to completion? And what algorithm should we use to schedule those jobs? So the algorithm we're going to use is to choose the job with the shortest time remaining. Now there are n factorial ways to schedule jobs, so good thing a greedy algorithm works here. And so the shortest one's going to be J sub 4, followed by J sub 3, followed by J sub 1, and J sub 8. J sub 2 with the time of 8. This will give us the minimum average time to completion. Now let's expand this a little bit. Let's assume that we have more jobs and we're trying to minimize the average time to completion, but they're allowed to run on 4 cores. What algorithm should we use? Well, luckily we're going to choose the job with the shortest time remaining, but iterating round robin through the cores. And so we would pick the shortest job first, J sub 4, J sub 9, J sub 3, J sub 11, and now each job has one job. Each core has one job running or scheduled for it. And then we go through and we schedule all of the remaining jobs here. And so again, there are a lot of possibilities and combinations. Luckily, a greedy algorithm gives us a quick optimal solution. Let's assume that you've been hired by an international web ordering company, say Nile, to design an algorithm to fit their various size products into boxes. Luckily for you, this company only has one box size. So what algorithm are you going to use to determine which product should go in which box? And will it produce the optimum or the minimum number of boxes? So let's first consider the scenario that the product is to be placed in a box before placing the next one. You can think of this as a conveyor belt of items, but you can only see one at a time. These are known as online algorithms. And so let's first talk about next fit. And so what this means is we're going to just fill the box until it's full. We're going to close it up and send it out. And so this is simple, fast, runs in linear time, but may require as much as twice as many boxes. So worst case is 2 to the n minus 2 boxes. Let's talk about first fit, where we find the first box that it will fit in. So we keep them all open and we're looking through them to find the first box that it's going to fit in. And all the non-full, we're looking at all the non-full boxes. If there's not a box it'll fit in, we're going to create a new box. This is simple, but a naive implementation is order of n squared, but an order of n log n is possible. It never uses more than 1.7 n plus 0.7 boxes. So that's pretty good. Let's talk about best fit. So place it in the tightest spot first. This is going to minimize leftover space, but not surprisingly, it uses the least number of boxes of the online strategies. Unfortunately, the worst case doesn't improve much better than 1.7 n. So fortunately though, there is a simple implementation that is order n log n and does better for random inputs than the other online algorithms. So we can do better, meaning use less boxes, if we knew all the products that needed to be shipped. These types of algorithms are known as offline algorithms. We could try all combinations of products that in all the boxes, but that would be a terrible idea because it's order n factorial. So instead what we could do is first fit decreasing, FFD. And so while there are a lot of published offline algorithms, let's just talk about a greedy algorithm that sorts the products by size and then places the largest products first into the box that minimizes the leftover space. It's simple. It uses at most 11/9 times the optimal number plus 2/3 of a box. So we're still not guaranteed to give an optimal solution. Another similar approach would be best fit decreasing, sort the inputs, and then apply the algorithm, but looking for the best fit. Well, thank you for watching. I hope you enjoyed this video.